Next section, Section 10, Transient Limit Monitors. This is something that we came up with hopefully to make your lives a lot easier in terms of doing these transient stability runs. So traditionally, to do a transient stability run, you might, set up a scenario, do your analysis, save a lot of data, so you've got this really large file, and you need to know if certain things happen during your run. So you're looking for certain conditions to be met, so you might have to write your own post-processing software to go through all this data and point out, if a voltage falls below a certain value or a frequency falls or below or exceeds a certain value. The benefit of doing this is that you have all of your results. So if you change your mind down the road and you want to go look at your results again, you can look at them for different criteria. You've also have this information available as to say that you did something. You've got the proof. I did all of this. I have all these numbers, so I must have done something. The downside is that you have all of this data, so you can get into lots and lots of storage of things maybe you'll never look at again. And we talked about the option earlier when you're saving data that maybe you're not saving everything every time step because you want to cut down on the amount of data that you stored. So in the process of skipping time steps, you may have missed something. So you may have missed a frequency dip that could be significant. What we came up with after talking to people of how they use transient stability and how they use the results, we came up with something that's kind of analogous to contingency analysis, where when you run a powerful contingency analysis, so when you do that, you're looking for voltage violations and you're looking for thermal violations on branches. You're not storing every flow and every voltage on every branch and bus. So we have two different forms of these limit monitors. We have something we call generic limit monitors that let you do very specific things, and then transient limit monitors that are customizable to study the things that you might be most interested in checking in your results. So the first thing, the generic limit monitors, these apply to synchronous generators. So there are three things that you can monitor with these generic limit monitors. The first is an absolute angle deviation. So it's the change in the rotor angle relative to the initial rotor angle for a particular generator. There's over-frequency and under-frequency monitoring. And then there's also an option to, if you have relays on generators, it doesn't make much sense to use these generic limit monitors, so you can use those mostly if you don't have, so you can use these generic limit monitors are useful when you don't have the relay models that have the actual information built into them. So let's go on into Simulator and take a look at where these generic limit monitors are defined and the options that are available for those. There's a case that we'll go through an example with these. It's called the WSCC_9 bus case. So if you want to go ahead and open that up, again, that should be in your transient stability folder, WSCC_9bus.pwb. The generic limit monitors, again, are back on our transient stability dialog. They're under options. So here you have the three criteria that we check for: the absolute angle deviation, the overspeed, and the underspeed. And for each of these, there's options of what to do when something happens. So if under this action to take field, there are drop downs. You can either ignore. So if you don't want to use this generic limit monitor, just leave it, set it, ignore. You can log the warning, and just basically that's going to show up in the message log and tell us that something happened, but we're not going to do anything. You can cause the generator to trip, or you can abort the entire simulation. And then each of these has a pickup value. So the pickup value is the value that needs to be exceeded in order for something to be considered a violation based on this monitor. So the default for the absolute angle deviation is 180 degrees. There's an overspeed and then an underspeed, and the defaults for the overspeed is 61.2 hertz and the underspeed is 58.2. And then the pickup time is the amount of time for which these conditions, the pickup value must be exceeded in order for whatever the action defined to happen. So if we go back.
So what's the basis for the default?
The basis for the default, I have no idea.
Because I think the defaults have changed. They've been tightened up from what they were several months ago.
I can't say where those came from. So slide 7 shows basically what we mean by the pickup value and the pickup time. You know, you start off, you've got some flat value, hopefully, when you start your simulation, and then you've got your pickup value. So if you, in this particular case, you fall below that, whatever the action is going to occur. You know, in this waveform example, we fall below the pickup value, but initially we fall below, we recover. So then for this first dip, nothing's going to happen. And then at some point, we're going to fall below that pickup value again. And we've stayed below that pickup value for the specified pickup time. And so now we've met our criteria, so whatever the action is going to happen. And then with the actions that are trip or open, there is also an optional breaker time delay in cycles. So if something's going to trip, you can also cause a delay of however many cycles before that trip action actually happens. And then there is one final value just to pick up. You know, if your system is blowing up, and you might as well just stop your simulation. There's this maximum allowable angle difference of 1,080 degrees. So if that happens, the whole simulation will just abort. There's no option of, you know, you can make this number larger if you don't want that to happen, but the only option that's going to happen is your simulation aborts.
Breaker delay time? As far as the default values, it would be interesting to know some basis for that, even if it's shaky. Most of the machines in the WEC dynamics file do not have under an open frequency protection in there.
Do you know where those defaults came from that are in here, the 61.2 and the 58.2?
Well, we went back and forth on default values. The problem is if you don't have anything, you can run into situations where you're running at 70 hertz and nobody knows it, and I mean the defaults are to ignore them. You know, you have to have something. Defaults are always tricky to determine because.
But I guess it's of interest to me to have, like, because I use these. And I use them to trip because I want some sign that, hey, there's a problem. And that's what I'll assume that they will trip. I just don't know what value and what the basis should be, so I go with the default. And if there is some, I don't know, idea that even if it's a wide range, if it's like a conservative range, at least then there would be some knowledge as to where the default came from.
Yeah, I mean, we did look to figure out the defaults, but I can't recall right now where we looked.
Okay.
I mean, we were thinking, I mean, they didn't just come out of nowhere. They didn't just, like, throw some numbers up in the air and, 61.2.
Yeah, but they did change, and that's what I noticed, that they changed from several months ago.
Oh, did they?
Yeah, so now, because it used to be that for the underspeed it was 57.6, so now it's 58.2. And for the overspeed, it used to be 62.4, and now it's 61.2.
And I don't know why the values changed. I will look in the code right now while Caroline talks.
And it'll probably just be different.
Well, I don't know.
Maybe there'll be a comment.
Sometimes we put comments in the code that Gordon wanted this changed, so.
There's comments like that.
Yeah. Gordon. Sort of things come up.
Okay, so before we actually set these generic limit monitors, so the first thing here, just make sure that all your actions to take are set to ignore, and then go ahead and click Run Transient Stability. And the thing we should see is, some nice happy plots here, except that problem with this case is that there's no governor here, so our frequency keeps increasing, but our rotor angles, seem to be stable. If we change our clearing time on our fault, so if we go to the simulation tab, and for the second action here in our contingency, take a look at this, the open both option here is set to happen at 1.077 seconds. If we change that to something somewhere between 1.079 and 1.08, we'll see a different result. So I'm going to change that to 1.079, and you can just type that directly in the field, and then hit Run Transient again. Oh, that didn't do anything different. Maybe we need to go a little bit higher on our clearing time. 1.08. Okay, there we go. Now we get some funky plot here that our system's unstable. So now we can use our generic limit monitors and see how those affect things. So before we do that, so I don't forget to do this, I'm going to put my time back to the original time just to see our stable system, 1.077. And then we'll go back to our options, generic limit monitors, and we're going to put the numbers in that are on slide 10. So we're going to change the over-frequency action to trip open, and we're going to change that to 61.3. And then the under frequency, we're also going to change that to trip open, and that can stay at the 58.2 value. And then our pickup times will be 2 seconds for both of those, and then no break or delay. So now, once we have that set up, if we hit Run again, our plots look a little bit different. This red line, which is our generator 3, it's going along and seems to drop off. And then our frequencies look a little bit better because instead of going off, they've fallen back down to closer to nominal. If we look at our events table, so if we look at the results from RAM and then the events, what we can see here is what happened, and we can see that our generic limit monitor took over. This model type maybe could be a little more descriptive, but this generic gen is our generic limit monitor, and it's telling us that we tripped generator 3 due to overspeed. So that's...
and if you click the transition, then I think you'll get the pickup.
Apparently not. Oh, when it started monitoring it?
Yeah.
Maybe you only get those for the transient limit monitors. I don't know. Or I haven't honestly played around that much with these options of what's included in there. Now if we change our, go back to our simulation page and change that clearing time to the 1.08 instead of the 1.077, and then run this thing again. So click Run Stability again. Now, looks slightly different than the plots in the slides, so just ignore those. But basically what's happening here, if we look at our events table again, there's 3 entries now. We're tripping all of our generators. Generator 2 and 3 initially get tripped on overspeed, and then generator 1 actually got tripped on underspeed. And at that point, we have no generators remaining in our case. So you get all these topology opens, which basically mean we've islanded all of these buses. So at this point, our entire system has been islanded, and we've really made a mess of things. So it's either that, or you could go unstable and leave your generators on, and if you could choose just to log that information, but it's probably more dramatic if you actually start opening things up, if that's what would really happen.
So the last one, solution failed, and so then that also would apply to the network equation not being solvable.
Right. If we go back to that table that Tom said don't look at, we should see some indication in here that our network solutions are, let's see, what do we got? Mismatches.
Yeah, be all the way down to the bottom. Those values on the high and low frequency were originally set to match the TSLF GP1 and GP2 defaults.
Oh, okay.
And then Jamie changed them on April 13th, 2010.
So they haven't been changed in the last 6 months. Okay.
No, they were 0.96 per unit, 1.04 per unit, and then he changed them to 0.97 per unit, 1.02 per unit, but he doesn't say why he changed them. I mean, they're just defaults.
Oh, shouldn't there be some big number showing up in here?
It depends where it crashed.
Maybe it...
What were you doing?
Well, everything islanded, so it probably occurred before it ever did the net.
What's the message?
The solution failed, aborted with error, no viable islands. So that probably checked it before it ever tried to do it.
That's not that wasn't the power flow network power balance did not work. That error comes when you no longer have any viable islands. You no longer have any islands with generation. So whenever there's topology changes, where you see topology processing open, it's going to check to see how many viable islands do it have, and we have criteria in there for what's a viable island. It can't be viable if it doesn't have any generation. So that's what's going on there. Yeah, so you tripped all your generators.
Right, yeah.
Yeah. So. Yeah, that wasn't the network issue. That was a topology processing check.
Okay, so that's the generic limit monitors. So there's another case we're going to use for the transient limit monitor, so let's just go ahead and open that. So File, Open Case, and we're going to use something called GSO_37 bus. Again, that should be in your transient stability folder in your training cases directory. And this is a case that has people that Tom knows in it are all the bus names. So if we go to back to our transient stability dialog, the transient limit monitors have their own section in here, have their own page. And the transient limit monitors allow us to take things a step further and to monitor quite a bit more than just those 3 things related to synchronous generators. We have some built-in transient limit monitors here. If you right-click on the transient limit monitor table, and you go to the transient limit monitor records, there's these build WEC Category B and Category C standard monitors. This case has the WEC one, the Category B, already added in here, but at any point in time, if you want to use these, you can also, build the Category C. Basically, if we take a look at what these are, hopefully there's people in the room that understand what these are supposed to be for, but if I right-click on one of these, so the WEC Category B voltage dip non-load bus, show dialog, the idea behind this one is that we're going to monitor all non-load buses for any voltage dip of 30% below the initial voltage value. And so this is going to occur any time that there's a dip. And it doesn't matter how long the dip is. It's just as long as the voltage falls 30% below whatever the initial voltage was. So how we've set this up in this dialog is through a bunch of options that we have. The things that you can monitor with the transient limit monitors are under the device type drop-down. So you can do, all the standard objects that you would probably want to monitor during a transient stability run. You can monitor branches and buses and generators and loads. So for this, we're monitoring voltage drops. So we want to do a device type of bus. And then for each device type, as you change that, there's a drop down for fields, so all the fields that you can monitor. So these are, the fields that you can select when you're selecting the results to store. So these are the same things that you can monitor with the transient limit monitors. There's a filter for monitoring. So generally, you're not going to want to monitor every device in your case. So you don't want to monitor every bus. So there's options. You can do all if you want. There's a meets filter. So the filter that you're meeting would be an advanced filter. So you define whatever the criteria is for the buses that you're monitoring. Load buses only. We've kind of built that one in for you so that you don't have to go through and build that filter. Non-load buses only, and then you can also use the area zone filter. So this is a specific WEC Category B that's saying I am monitoring non-load buses. And I have a feeling the reason we added the load buses and the non-load buses options was because we talked to you guys and folks in WEC to know what kind of criteria things you monitor. So we've added those. If there's something else that comes in as something frequently monitored, we're always open to adding other things in here, so you don't have to, make the advanced filter yourself. The action to take with the transient limit monitors is again similar to what we had with the generic limit monitors. You can choose to log the violation only, so you just want to know when this happens and take no action. You have to do something because of it, but you don't necessarily need to affect your simulation as it runs. You can abort the entire simulation, which is a little drastic, but maybe you want to do that. Or you can trip and open the device, again, similar to the generic limit monitors. I suspect with most of these transient limit monitors, you're probably just going to log the violations because this is analogous, again, to any post-processing that you would have written yourself to analyze all the data. So this is going to tell you when this happens and really take no action. There's a maximum number of violations of this monitor to store. So, you know, if you only need to know that this happens once for any bus, then you can change that. If you want to know that it happens a lot of times, you know, you can make this number larger. It just depends, again, what your criteria is for what you're monitoring. The limit value, again, defines, there's a little chart over here. That's the thing that you're trying to exceed, either go above or go below. So because we're monitoring a voltage, we're saying when the voltage drops by 30% of the original is what we're saying here, then I want to do something. And again, the limit duration is the pickup time that we talked about with the generic limit monitors. How long does this have to happen? For this particular criteria, it doesn't have to happen for any period of time. It just has to happen. And so as soon as it happens, we're going to log this. Here we do let you change that pickup time. There is an option here for between seconds and cycles. So we were thinking on that one. And then the limit type is whether it's a lower limit or an upper limit. So are you dropping below this value, or are you going above this value to consider something a violation? And then the meanings of the value specified. This lets you be very flexible as far as what you want to enter in here. So if you put in an actual value, then of course that's an actual value. So for a voltage, if you put in 0.9 and the limit type is lower, then as soon as your voltage falls below 0.9 per unit, then this limit monitor is met. The percent of initial value, so it's when it meets whatever percentage of your initial value is, the deviation or the percent deviation from the initial value. So in this particular case, it's saying when the change is 30% less than the initial value, then that's when this condition is going to be met. So you could specify if you want to do a deviation or an actual value, you can make, put the same values in to mean the same thing. It's how you want to present things. And then there's some top secret options here at the bottom. If you click this show special triggers. So this, if you don't want to monitor constantly, these are triggers to say when you're going to start monitoring things. If you remember yesterday, let me cancel out of here. If we go back to our options, result options, there's this time to begin checking for limit monitor results. So that's by default set to after the last event. If you want to be more specific than that, that's what these special triggers are for. So normally these are hidden because most people don't even care about that. So I'm not really going to talk about them other to say that they're there if you think you might need them.
But this must have been user requested?
Of course, yeah. Somebody maybe thought they needed it and really didn't need it. And after they started playing around with it, thought, well, okay, still there, but okay, so that's the basics of that. So again, if you go through these device types, you can see all the different things you can monitor. I'm just going to cancel out and leave this the way it is. If you look through some of these other criteria that are built in here, there's a voltage dip for load buses category. And I'm assuming these are still valid WEC categories, is that?
Yes.
Okay, so for a while, are they changing?
I think we would adopt the NERC, so they'll probably go away, right?
Yeah.
DPP will go away.
But this was specific for WEC.
Right.
And then there's the addressing, I can't remember if it's WEC 001 draft. It's the one that I think Chuck Matthews is on. And so then it's going to be changing actually be simpler to monitor, because it's not going to rely on a dip, but rather the duration for the whole fault period.
Okay, so anyway, if you want to see the details of these and how we've defined them, you can go through these examples. So, it might help, because if you understand what these criteria are to relate to how we've defined those here within simulator. So, and for this example, we're going to enable all of these WEC Category B transient limit monitors, and there's also a generator out of step one that we've added for this example. So let's just take a look at that real quick. So if we right click and choose show dialog on the generator out of step, what this one is doing, it's monitoring a generator, it's monitoring the rotor angle no shift, so that's the one that looks like it's probably going to go off to affinity. We're only logging the violation. The limit value is 180 degrees, but we're checking a deviation from the initial value. So what we're checking here, and it's an upper limit. So if the rotor angle increases by more than 180 degrees from whatever its initial value was, then we're going to trigger this as a violation and report that. There's options with the limit monitors to make them inactive if you want, so you can define a bunch of these and choose not to use them in a particular study. So let's just go through. I'm going to right click in the active column and choose set toggle columns and toggle all yes. We'll enable all of these, and then we'll just hit run transient stability and see what happens. So if we go, let me close my plots here. If we go back to the simulation page, and we've had several questions on this information that shows down here in the bottom right-hand corner, the transient contingency monitor violations. So that's what you get as a result of using these transient limit monitors. You end up with transient contingency monitor violations. So this is reporting any time that any of those transient limit monitor criteria are met. And we can see that same table maybe a little more clearly if we go back to the transient limit monitors page and then click on monitor violations. So this will show us for any of the transient limit monitors. So the transient limit monitor name field tells us which limit monitor is being violated for which contingency. So if we had multiple contingencies, we might see multiple contingencies in here, but you can filter and only show one contingency. The violated device, so with these frequency monitoring, we are monitoring buses, so it stands to reason that that's the thing that's going to be violated. And then the generator out of step, we have generators, and then I think those are the only two types of transient limit monitors that are met. And then we get a bunch of numbers over here. So the best way to find out what those numbers are is to reference slide 25. That's a handy-dandy key to knowing what you're looking at here in terms of a nice little chart as well. So for any of these limit monitors, there is the actual value and the time of value indicates the value of whatever it is you're monitoring at the time that the limit duration is met. So if you look here on our little picture, we have a limit value, which is our line here, and our trace of our values. At point A is when we meet our limit value and fall below our limit value, or above if it's an upper limit. And then if we keep decreasing, we stay below the limit value for the limit duration, which is point C, then something is going to show up in the transient limit monitor dialog. So that's the actual value, and the time of value is what the value we're at when we've met our limit duration. The actual value start and the time of value start is when we've met our limit value, and that's the point we're going to start recording of whether or not we're going to meet our limit duration. The actual value extreme and the time of value extreme is the low point or the high point, depending on what you're monitoring. And then point D, which is the actual value no longer and the time no longer, that's the time at which you would go above your limit value and no longer, be exceeding whatever that limit value is. Point D might never occur. So, you could just keep going down, down, down and never come back up. So you may see that for those values, those might never be filled in. So if we look at our actual results here, we do see that for our generator out of step criteria. We do not see the actual value no longer is filled in. There's extra values here, these converted values, and I am always confused myself what they actually are. That's something fairly new, and we need to add a slide in that. So it's some combination of what the meaning of you've chosen to meet the values to mean. So I think in this case, the converted values and the actual values are all the same, but if you change the meaning of your limit values, those might be different. Well, actually here, the actual value extreme and the converted value extreme are different.
So there's on the dialog for the transient limit monitors, then there's the box for meaning of value specified.
Deviation. Converted value extreme, actual value extreme. So that's an absolute. I'm not sure, and I'm not exactly sure why they're useful. We'll have to leave that one. I've had it explained to me before, but obviously it doesn't mean anything because I don't remember it. I'm sure it means something to someone because that's why we've added it. Then the last thing that's useful to do with the transient limit monitors is you can actually define plots from these. So if you select some, I think you just have to select rows because it's going to create plots of the object that was violated and the value that you're monitoring. So if you just select some rows and right-click and choose Transient Limit Monitor Violation Records, make a new plot, it will make a plot of all of those objects and values and fields that you selected. So something useful to do, I guess, with the transient limit monitors is you can do your first run possibly just not monitoring anything. You can have all of your results to store options set to don't store anything and just run analysis with your transient limit monitors, which then will give you an indication of the things that you want to actually store maybe the next time through, because those are the things that are going to be relevant. The transient limit monitors we mentioned, I think, earlier when we talked about when you're setting the results to store options, you have the save results every n time steps. That doesn't apply to the transient limit monitors. We're monitoring things every time step. So with the transient limit monitors, we're not going to miss anything. So I think that's all we should need to cover on this.